Hello and welcome to N31, our continuation of intermolecular forces, focusing on vapor pressure and phase diagrams as how they are affected by IMFs. So, first thing getting into is equilibrium vapor pressure. Basically, vapor pressure is the pressure of the vapor at equilibrium. So we are looking at right above a liquid. We're not talking about atmospheric pressure. We're talking about the vapor of a liquid that is at equilibrium. So it's occurring at the surface with the equilibrium of the liquid continually. This is ultimately determined by the size of the IMF in the liquid. So looking at, are they stronger forces or are they weaker forces? Vapor pressure tends to increase significantly with temperature. So as temperature is going to go up, molecules are going to leave the liquid state and go to the vapor state within the vapor pressure area, not going to gases out and away from the solution, but then staying right there at the equilibrium, just having more vapor pressure as temperature increases. Volatile liquids have high vapor pressures. Volatile liquids tend to have very, very low boiling points. So hydrocarbons, low hydrocarbons, methane, that's a gas more often than not anyway, but propane can be a liquid, hexane, some of the alcohols again are considered volatile liquids because they have lower boiling points. And then reminder, boiling point is the temperature at which vapor pressure equals atmospheric pressure. So again, a liquid is not going to boil until its vapor pressure equals atmospheric pressure, wherever it may be on the planet, and then boiling can occur. Questions on equilibrium vapor pressure? Alrighty then. So continuing with vapor pressure, the pressure exerted by vapor when it is in a dynamic equilibrium with its liquid is called vapor pressure, as we've kind of already been talking about. Big thing to remember here is the use of Dalton's law of partial pressures. Basically, when you collect gas with water, water is going to have a vapor pressure included with the gas you produced by a chemical reaction. So, biggest mistake students tend to make on the AP exam is forgetting to subtract the partial pressure due to water vapor, because water has a vapor pressure usually given at whatever temperature you are at. Weaker attractive forces between molecules, the more molecules will be in the vapor state. So higher vapor pressure when you have a weaker IMF involved. As we just said, weaker attractive forces, higher the vapor pressure. Higher the vapor pressure, the more volatile the liquid. So just to say something is volatile, okay, that fits with having a low boiling point. But when you're comparing a bunch of volatile liquids, therefore you have to figure out and rank their IMF in order to rank them based on vapor pressure and which one is more or less volatile. Questions on this? Okay. Vapor liquid dynamic equilibrium. If the volume of the chamber is increased, it will decrease the vapor pressure of the vapor inside the chamber. So at this point, there are fewer vapor molecules in a given volume, causing the rate of condensation to slow. So you got to realize that there is an equilibrium occurring at the surface, and you can mess with it. As in we just said, temperature earlier is going to increase vapor pressure. If you mess with the surface area or the volume of where this is happening, again, you affect vapor pressure it can go back into the liquid. So again, it is an equilibrium. It can be treated like an equilibrium. Le Chatelier's principle plays a role here. So got to be aware that even though it's looking at the surface of a liquid, Le Chatelier and all our ideas of equilibrium that we saw last semester are going to play a role. Which then also goes to kinetics, because you can kind of change the rate of the direction it's going. Once you're in equilibrium, rate forward equals rate reverse. We know that one. For our purposes here with the vapor-liquid equilibrium, we're looking at vaporization going into the gas state versus condensation going into the liquid state. So depending on what you've messed with, what you've done, one of those rates can speed up, producing more or less vapor, or producing more or less liquid. Again, depending on how you mess with the equilibrium. Eventually, enough vapor accumulates so the rate of condensation increases to the point where it's once again as fast as evaporation or vaporization. So just like Le Chatelier, it will shift in the direction to undo any stress to get back to your dynamic equilibrium. And then the vapor pressure will be the same as it was before. So in this situation with this specific equilibrium, again, assuming temperature is held constant, it will go back to where it was before any stress was applied, of messing with the volume, adding more here or there. So got to keep in mind that still follows the same rules as equilibrium, but the vapor pressure should return to the same as it was before any kind of change in your rates of condensation or vaporization. But as long as temperature remains constant, it will go back to this point. Any questions on vapor-liquid dynamic equilibrium? Okay. So our heating curve, we're all familiar with this with thermochemistry. Nothing new here in this sense. We know what's going on. We know temperature is going to remain constant during a phase change. This kind of comes up because our green line we see here, kind of the top middle, water and steam, that is where vapor pressure is kind of existing at that point. And then obviously we can do delta H calculations if needed, depending on what's going on. So kind of a little review-ish, if you will. All right, phase diagrams. College Board does not put a huge emphasis on phase diagrams. They kind of show them. They might have you guys, they might put letters on the diagram, A, B, C, D, E, and maybe ask you a question about which letter represents a certain part. But ultimately, a phase diagram represents phases as a function of temperature and pressure only. So that's kind of the main purpose of a phase diagram, to know how the phase of that substance is going to be affected by either you changing temperature and or changing pressure. There's this point called the critical temperature. Any temperature above this critical temperature, the vapor cannot be liquefied. So I have some diagrams coming up that will make reference to the critical temperature, but interesting, you get to a certain temperature based on the substance and its chemical makeup. Doesn't matter what you do. Once you're above that temperature, you can put 1 billion atmospheres of pressure and it will stay a vapor, or it will stay a gas. The critical pressure required to liquefy at the critical temperature. So again, when you're at the critical temperature, there is a critical pressure. When you're above the critical temperature, there's nothing you can do. So again, X axis, Y axis meet at this point, and then we know what's going, or what the pressure is needed to convert it back to a liquid. For water, It's 374 degrees and I think some change, which equates to 218 atmospheres of pressure in order to do that. So the minute you get to 375 degrees Celsius, water, again, you can turn the pressure up to 8 billion, it will stay a vapor. So just kind of a generic phase diagram. We all know the states, solid, liquid, and gas. We should all know the processes at each line. If you're on a line, you're in equilibrium with those two phases. We should know how delta H, being exo or endothermic, is playing a role with all these processes at each line. And up here at the top right, here's our critical point. Notice the line stops. It does not extend past this point. So whatever this temperature is will equate to a pressure. That is the critical point. But anything beyond that temperature, see the whole green area on this graph, cannot change it. It is a gas forever if the temperature remains above that point. So here's water. We can kind of see its phase diagram. Again, 218 atmospheres or 374 degrees. The triple points right there, smack dab in the middle. All three states coexist at the exact same time. Kind of a cool thing to actually see. But again, no matter where you are on the graph, if you change pressure and or temperature, then you can change the state that you are in. Here's another one, carbon dioxide. Again, very different. Its critical temperature is 31 degrees. So once you are above 31 degrees, carbon dioxide will be a gas no matter what. Its critical pressure, 72.8 atmospheres at 31 degrees. So again, a reference to that. Triple point, way down there. You can actually do this in the lab and create the triple point, which is kind of cool. But an interesting thing to notice, let's go back for a second. Here's water. Notice the equilibrium line between solid and liquid of water. Now here's carbon dioxide. Again, notice the equilibrium line between solid and liquid carbon dioxide. Here's water. Here's carbon dioxide. Here's water. Here's carbon dioxide. So hopefully you noticed water is a negative slope. Carbon dioxide is a positive slope. Now the interesting thing here, water is one of the few substances that we know of that actually has this negative slope. And avoiding the math and the craziness, basically what it has to do with is we know that the solid form of H2O is less dense than the liquid form of H2O. And that less denseness, if you will, ice, floats in itself as a liquid, does come about because of this graph. Whereas carbon dioxide, if I put a chunk of solid carbon dioxide, dry ice, into liquid carbon dioxide, it's just going to sink. Most substances, as a solid, will sink in their own liquid. So just one of those little FYI things. You can look up the Clausius-Clapeyron equation on your own, which does explain the math of it, if you so choose. Here's carbon, i.e. diamond or graphite. You can see the pressures are way up there and the temperatures way up there in order for these things to exist. But yes, you can take graphite and apply a crap ton of pressure at 2000 Kelvin or even 4000 Kelvin and create a diamond. But you can also take a diamond and lower the pressure and make graphite. So you're able to kind of go in either direction if you so choose. Here's sulfur, just another one to check out. Interesting thing here, its structure of sulfur actually changes from a rhombic structure to a monoclinic structure. Again, don't worry about structure and materials, but just it's interesting. Sulfur has two different solids, before it gets to the liquid state or the vapor state. So just one of those, everything is a little bit different. And that will be it for today. Thank you very much, and I'll see you next time. The notes for the rest of this are more of FYI, which you can look at that in the PDF on the website. Thank you much. Peace.